do lecture 5.3. Yeah. So remember when we met last, which was like a week ago, we learned how to sketch the root locus by hand, which I said was great because we needed to learn how to get an intuition for how if the transfer function or the poles and zeros in the transfer function change, how the root locus will change. Remember, the root locus is a plot of all of the locations of a closed loop system given different gain values, all possible gain values. So for the loop. So this is very important for doing our controller design, and generating the root locus via a computer allows us to be more precise about it. So we can get an intuition through sketching, and we can get a precise root locus using a computer like Matlab. That's what we're going to focus on. I'm still in discussions with the registrar about how to do the final exam in one of these computer classrooms, but that is my goal. Okay, so we're just going to do Matlab. You can do this in Python too, but the feedback I get on Python is that it's less user-friendly for students to use. So I like to be user-friendly for students. I always try to go for that as a goal. Kind of a reach goal, you know. Sometimes it doesn't have to be that way. All right, so let's focus on Matlab. So in Matlab, the command rlocus generates a root locus plot from a linear system model object defined by one of the three commands that we've learned to define these linear system model objects, TF, ZPK, or SS. So if you have a transfer function with polynomial form, so in descending order of powers of S, then TF is your way to go. If you have it factored out, if those polynomials are factored out, you can see the zeros and the poles, or if you just know the zeros and the poles. The open loop transfer function, define it with ZPK, and we'll do an example of TF and ZPK in class today. Or SS, if you have state space model with your A, B, C, D matrices, which we learned to generate from the linear graph modeling technique that we learned. Okay. The data cursor in Matlab has particularly useful information associated with it, including the gain required for the closed loop pole of a given branch to be located at the selected point. So that is interesting information that we don't necessarily know. We don't know by just looking at the plot. So it has that information. And the reason it has that information is that how Matlab generates the root locus is it says, oh, what if your closed loop gain was 1.23? And then it just does a numerical solution for the poles and zeros, because as you just find the roots of the numerator and denominator of the transfer function numerically, which is pretty easy to do. And then, it's not too bad if you're Matlab. And then you can, then it just plots where those poles and zeros are. So there's a point. And then it does the next one, there's the next point. And the next one, there's the next point. And it just does that. So it knows what gain is associated with each of those points because it used some gain to generate the point. So it's really easy to have it say, oh yeah, this point that we've got on the root locus here, that was generated using this gain. So it's pretty nice. Great. So here are a few examples. So we'll use ZPK here. So this is the open loop transfer function, and that's what you give to Matlab, and then it will compute the root locus using the rlocus command. So this is all in your notes filled in, so you don't have to copy down a bunch of code, which is hard to write, I know. So ZPK we use by putting in the 0, -10 from this term, -5 from that term, -15 from that term, and -20 from that term are our three poles. And then it has a gain of 1, so that means it's 1 times this. If it was 7 times this, then this would be a 7 instead of a 1. So that's our ZPK system model. Okay, so figure opens a new figure in Matlab. If you don't include this, our locus will either open a new figure if there's no figure open, or it'll just merely use the last figure that you had open and overwrite the plot, which is usually not what you want. So that's why I put figure in there so that it opens a new figure, and then it'll write our locus of sys on there, and something like this is generated. Let's actually do this in Matlab. Where is my Matlab? You do need the control systems toolbox.
Oh, okay. That's where it is.
Yeah, control systems. That's supposed to be a Y. Systems toolbox. Yeah, it's the most useful toolbox if you do control systems. I know, it's very strangely named. 30?
Yeah.
Yeah, that sucks. Yeah. Yeah. This is why I want to do MATLAB. I want to do Python. And yeah. Maybe next year I'll go to Python. I did this once when I taught the ME315 class, the instrumentation and measurements class, but the students really didn't like me very much for that. They were very not cool with it. So, well, I don't know. All right, so there was our ZPK command. So that's easy. And then figure our locus. And there's our root locus. Nice, huh? Pretty easy to do. Just grab our data cursor here and we'll pop it on there. So let's interpret this for just a moment. I hope you guys can see that okay. I know the font's kind of small. I don't know of any way to make it bigger. So this data cursor has the ability, so if you just use up and down arrows, it'll move it along from one point to the next. What you see here, the first row is the gain. So gain of 750 at this point, gain of 665 at this point. So what that's saying is we computed the closed loop pole locations using a gain of 665, and this was one of them. There's also going to be another one that corresponds to that down here. Let's see, 665, complex conjugate pole pair, right? So when the gain's 665, there's a one pole up here, there's one pole down here. There's going to be one on this branch too. Let's see where that one is. There's our gain of 665. So these are going to be our three pole locations when the gain is 665. Yes?
And the gain is what you would use to get there linearly, right? To that point, you need a linear...
What the gain does is the gain that we put in our controller. So remember the controller block diagram that we're using here. We've got our controller, we've got our, we've got our plant, we've got our summing junction, unity feedback, unity negative feedback, negative, there's our command R. This is our controller with gain K, and then here's our plant, call it G. So this is our block diagram. So what we're saying is, if you have a gain of K, the closed loop transfer function from the command R to the output Y is going to have, it's going to be something with a polynomial and S up here. It's going to be something with a polynomial and S down here. And if you find the pole locations in closed loop, then they're going to be at these locations. If you choose a gain, if you choose k to be 665, if you choose a gain to be, say, 750, then that's different. So 750, 750. So these would be the 3 pole locations in closed loop. So what it's saying is the closed loop pole locations, given different gain values, are what we see as the branches of the root locus here. And when we look at the plot, we don't necessarily know what the gain is that's associated with each of these points. But since Matlab used the gain to calculate that point, it knows the value and it'll give it to us. We're going to look at another way to find it analytically and graphically in the first lecture of next chapter. What's up?
How do you move up and down along the line?
Up and down arrows.
Yeah, that doesn't work.
That doesn't work for you? It didn't work for me this morning. I don't know why it's working for me now.
It brings
You back to the command window?
Command window.
Yeah. I don't know why that is. That happened to me too.
Did you click on the line search?
Yeah.
Yeah.
Doing anything special for this?
Yeah, I mean, I might have done something special. I don't know what it was, though. I feel like
Drag it around.
you can also go left and right, too. Left and right works for me right now, but earlier this morning, yeah.
Back and forth between-
Yeah, that happened to me, too. I do not understand that. It's probably like a Mac version of Matlab glitch or something, because I don't know. I didn't get it. Maybe there was something I was doing differently, but I honestly don't know. Yeah, you just make sure everything is selected. I mean, that's what I did, and it we didn't work this morning, but it is working now.
Everything's selected and what?
Meaning I click on these. So once you click with the cursor, you then get this grabber pointer. Oh, I guess I have to go back to the cursor. Yeah, it's always under the cursor. Whoa. So anyways, let's look into this a little bit now that I've got 50 of them up conveniently. Okay, so ignoring that one. Ooh, good, I can move it away at least. So gain of 750 is the first row. So it says that if you want to have a closed loop pole at that location, you need to have a gain of 750. That also implies that these other poles are at these locations, right? It doesn't say that, but when we put the data cursor around, that's what we find. So 750. It gives you the actual pole location with a few significant digits, which is kind of nice. Complex pole location value. It gives you 3 parameters here: damping, percent overshoot, and frequency. Okay? So what does it mean by those things? So we've got a third order system, okay? So because we got 3 poles, right? So if you have 3 poles, it's a third order system. It's not a second order system, but it's giving you second order parameters. The damping ratio, the frequency is actually the natural frequency. Don't know why they didn't put those next to each other. And then the percent overshoot, okay? Those 3 parameters are related to our performance characteristics from chapters 2, 3, and 4, specifically the transient response ones from chapter 3, okay? So the performance based on the second order approximation is given here. Now, that part is very important. In this system, is the second order approximation a good approximation? What do you guys think?
You got this collected.
Yeah. So, what do you guys think? Good approximation, bad approximation? How do we know?
In general, or for this one?
Well, I mean this one specifically, but how do we know in general if we don't know this one specifically? Okay, so
I think it'd be different.
yeah, so the idea is that you've got to have a pair of poles that are closer to the imaginary axis than anything else, any of the other poles or zeros that show up. So you have a complex conjugate pair of poles that show up here, which is second order like, right? This is a second order pair. But you've got this other one over here. It's closer to the imaginary axis. We said in our like second order approximation, rule of thumb sort of thing was that you should not trust the second order approximation unless your other poles and zeros are at least 5 times further to the left. This one's even to the right, so it's the opposite of a good approximation. It's definitely a bad approximation, but that won't stop us from using it. It'll just make us extra cautious about trusting it, okay? So we'll probably still use a second order approximation, but we're not going to expect that we're going to get good design values. So for instance, say you wanted to do a settling time that said that your damping should be 0.5. Well, this gain of 750 would get you a damping ratio of about 0.5. Okay, so that looks like a good gain, but when you are going to simulate this, which is what I always recommend doing, unless it's actually a second order system with no zeros, which it's usually not, do the simulation and check to see if your performance criteria are actually being met. So see, is the damping ratio really coming out to be 0.5? And you can check that using the step info command. So the step info command is your friend here. It'll give you things like rise time, settling time, etc., and percent overshoot. And these things are related to the damping ratio and natural frequency as well, which, remember, we have the second order approximation to guide us, but that second order approximation is rarely perfect. So we do need to use the step response to actually measure these performance characteristics, the transient performance characteristics. So let's keep that in mind. We're gonna read this off, but Matlab is assuming you're gonna use the second order approximation, and it's not saying that this is gonna actually turn out to be the percent overshoot, 16.5. You're gonna choose a gain of 750. Do we have time? Let's just do it. So if you want to do this is the part that I didn't prepare. So sys closed loop is going to be feedback of let's do the open loop, which is sys, and times the gain, which I said was what, 750. Unity feedback. So there's my closed loop transfer function, and let's do a step response. So let's do y step equals step of sys closed loop. Okay, and then let's look at the step info. So y step info equals y equals step info of y step. And I got a settling time of a percent overshoot. Where is it? 14.14. So actually wasn't terrible, but it was certainly not what it said, right? So 16.5 is what it said. Using the second order approximation, in reality it came out to be 14.13. So you can't trust it based on those values. They're always using the second order approximation. It could be way worse too. It could be significantly off. So if you guys just want to see that, for instance, and I'll show you guys how to do all this, don't worry. Plot y step. There's the step response. It's given. Fun, right? If I was to go back, I'd probably specify a time range and go longer, because I don't think that was quite sufficient to capture all the step response. But yeah. Okay, cool. So MATLAB's our friend. We can do all kinds of cool stuff with it, including checking out the gains associated with different closed-loop pole locations on the root locus. Okay. All right. Let's take a look at the next example. So use MATLAB and the TF command to generate a root locus plot from the open loop transfer function given here. Okay. Following code generates the root locus plot. So what I did is I said, okay, now this is in polynomial descending order of powers of S form. So I'm going to use TF instead of ZPK. It's just easier, right? I don't need to calculate what the poles and zeros are. I can just give it the coefficients of the polynomial and move on. So I did that. Bang, bang, bang. And then I decided to do this. You don't have to do this, but sometimes you're interested to put in some custom gain values. So when you use our locus, MATLAB just chooses gains for you. They're usually pretty good. But notice that when we were here, we wanted to change the gain. Like you go from 750 to 846 here. It's a big jump in gain. You might be interested in points in between there. So if you want to specify gains, like a more densely packed gains in a certain range, for instance, this can be useful. And you can add in, like I was like, okay, let's see what a gain of 3.5 specifically is going to give us in terms of the closed loop pole locations and in terms of the second order approximation performance criteria info that pops up there. So I include that in. Log space is pretty important when you're doing these root locus plots because logarithmically spaced lines tend to get you further down. And so if you do like a linear space out to 10,000, it's going to look a little bit funny. If you go out to 10,000 using a log space, it'll usually look a lot smoother. And then I also included infinity, which you can include in your gains, which should take you all the way to the open loop zeros or zeros at infinity. And if you do sort, that will help it not look crazy. Great. Open another figure. When you call the our locus command this time, you include those gains that you specified. Okay, and that one gives you one that looks like this. Once again, you could go along with the data cursor and find, what gain would be required. In this one, if you have too low of a gain, you're actually going to be unstable. The open loop system here is unstable. There are two open loop poles that are in the right half plane. So we need to move them to the left half plane by increasing the gain, which would bring us over into a stable region. Okay. Any questions on generating root locus plots in MATLAB? We're going to do it a lot, so you guys are going to see this. We're going to do this at like pretty much every lecture here on out. So it's like a first building block, and we're going to keep building from there.